Okay, so let's close this up and let's talk about nilpotent matrices. Are you ready? So we will start with the definition of a nilpotent matrix, which is a matrix that when we raise it to some power, it will become the zero matrix. And there are some definitions, we will go throughout it, but let's show you an example of it. So we'll talk about it. An example of nilpotent matrix is something like this. You can see that there is a matrix, it's just a matrix, but when we raise it to some power, and I don't say which power it is, but to some power, we get a zero matrix. So by definition, we need this power. This power is called the nilpotent index if it's the minimal power to the matrix that will bring it to the zero matrix. So for example, for this A, I know that this is a nilpotent matrix because there is some power to the matrix that gives me the zero matrix. Now, again, the minimum index, the minimum power that gives me the zero matrix for this matrix is called the nilpotent index. As you can understand, if I will take a to the power of 4, a to the power of 5, a to the power of 6, they will all be zeros. But the nilpotent index is only 3 because this is the minimum power that will bring me to the zero matrix for this matrix. Okay? Now, another very important idea of these matrices is that the characteristic polynomial, maybe need to start by this. The characteristic polynomial of these matrices is very unique. Characteristic polynomial of this, it's just x to the power of the nilpotent index. You see that this will be x to the power of 3, for example, because remember Cayley-Hamilton's theorem that states that matrix always annihilates its characteristic polynomial. And we know that characteristic polynomial is a mnemonic, and I know that this matrix annihilates x to the power of something because it's a nilpotent matrix. So you can see that this is the characteristic polynomial of A. Lambda to the power of 3 or x to the power of 3, whatever you want, but this is the characteristic polynomial of nilpotent matrix. X to the power of something. Something what? The nilpotent index. This is the power. Now, this is very important because if you think about the eigenvalues of those matrices, for this characteristic polynomial, it will always be zeros. Namely, for nilpotent matrices, the only eigenvalue is the zero factor, right? Zero value. So the only eigenvalue of nilpotent matrix is zero. This is another property that we just learned about. So we know that the multiplication of the eigenvalues of a matrix equals what? It equals the determinant. And if all the eigenvalues are zero, of course, multiplying zero will give you zero. So the determinant of a nilpotent matrix will always be zero. Now for the trace, remember that there is also the relationship between the trace of a matrix and its eigenvalues. The relationship is that the sum of the eigenvalues of a matrix equals its trace. So you know that the trace of a nilpotent matrix is 0 plus 0 plus 0, etc., depending on the nilpotent index of the matrix. So it will be also 0. So the trace of a nilpotent matrix will be 0. Very important. Because if I give you an example of a nilpotent matrix with non-zero values on the diagonal, okay? So let's see an example. You see that it's impossible to have a nilpotent matrix with non-zero entries on the diagonal. So diagonal entries of a nilpotent matrix in any basis within upper triangular form must be 0. So can I have a base in which the nilpotent matrix is not in triangular form? So I can have this. As you can see, I do have values on the trace on the diagonal, but this is true when we are talking about a triangular form. When we are not talking about triangular form like this one, so we have non-zero value on the diagonal. This is what I wanted to show you. And when you see that those are the values, if you take -1 plus 1, you get 0. As we said, the trace of a nilpotent matrix, and no matter if it's triangular, non-triangular, it will be 0. Okay? So let's continue. Let's see an example of a very important triangular matrix. Let's bring it so you will be able to see the very important one. I want to show you this. Here it is. I will show you in a minute. Just hold on a bit. Okay. So this is what is called maybe I'll go to Gemini because it won't work. This is the explain me on such matrices. This is what is called the shift matrix. It takes a vector and shifts it. And we will see it just a bit how it shifts vectors. First, you see that this is an nilpotent matrix. How do I know that it's an nilpotent matrix? Because let's see what are the powers of this matrix. To the power of 2, you can see that we start with ones on the superdiagonal, and this is what is a property um, of the shift matrices. Also, you can see that the eigenvalues are 0 right away because and characteristic polynomial is, as we said, x to the power something right away because the determinant of a triangular matrix is just take the lambda on the diagonal and multiply. So the characteristic polynomial of this is lambda to the power 4. And again, each matrix satisfies or annihilates its characteristic polynomial. So a to the power 4 will be 0 because the characteristic polynomial is lambda, x to the power 4. So it must be 0, but our question is if it's a nilpotent matrix, and we know that it is a nilpotent matrix because I just told you that its characteristic polynomial is lambda to the power 4. So if you put in the matrix A, you'll get a to the power 4 equals 0. So this is a nilpotent matrix by definition. There is a power for which the matrix becomes the 0 matrix. Okay? So now I want to show you that if I take this to the power 2, what happens is that the ones going from the first superdiagonal to the second superdiagonal. And when I take to the power of 3, again, we will move on. This is a characteristic of the shift matrices. So you can see how it goes. We start by this, going to this way, and it becomes the 0 as we just anticipated. So this is a nilpotent matrix because there is a power for which it annihilates the power for which it becomes the 0 matrix. Okay, so what is unique in this matrix? As you can see, it just shifts a vector some slots to the left, let's call it. So you see that if I take the matrix and take the E1, are shifted to the left and it becomes 0, 0, 0, 0. If I get A and I get here 1, again, I shift it to the left and this becomes E1. If I take, for example, here and A, again, shift matrix shifted to the left. Now, if I do it twice, namely A to the power of 2, it will shift 2 slots to the left. If I take A to the power of 3, it will shift 3 slots to the left, and this will become, for example, the 0 vector. Okay, so you can see the shifting of the matrix. This is why it is called a shift matrix. Okay, this was about this important matrix, about this shift matrix. It's a nilpotent matrix, eigenvalue 0, determinant 0, trace 0. You saw how it behaves with its powers, and you saw that it's a nilpotent with each characteristic polynomial being x to the power 4. And again, because of Cayley-Hamilton theorem, it must annihilate this x to the power 4. And we saw that its nilpotent index is 4 because a to the power of 2 is not 0, a to the power of 3 is not 0, a is not 0. So the first power by which this matrix becomes 0 is 4. So the nilpotent index is 4. Okay, so we continue. This was a very important thing. Let's continue. The next thing that I want to show you is an example, again, of a nilpotent matrix, a little bit bigger, but important one, because we'll see how to work with this. Please show me what will we do with that? What is the nilpotent index of this matrix? Okay, so we have a very big matrix, so 8 on 8, and we want to see what is the nilpotent index. You can see that mostly there are 0 here 1, here 1, here 1, and here 1. Maybe in order to show you this, I'll just go to graph, and there I have the solution. So here it is. Here it is. So this is our matrix, right? Now I ask, what is the nilpotent index? It will be quite hard to take this matrix and raise it to the power of 2, 3, 4. You can do it, but it's quite hard. If you understand how this matrix works, you will understand to the power of what, and if it will become 0, and what its nilpotent index, okay? So how this matrix works? It takes A E1 and shift it to 0. It takes A E2 and shift it to E1. It takes E2 and shift it to E1. It takes E2 and shift it to E1. It takes E3 and shift it to E2 because of this. It takes E1, 2, 3, 4, 5, 6, 7 and shift it to 8. And shift it to E6. It takes E1, 2, 3, 4, 5, 6, 7, 8, and shift it to E7. Okay, so, oh, it takes, sorry. It take E2 and shift it to 1. It take E3 and shift it to 2. It take E4 because this is the fourth column and shift it to E1, 2, 3, 4, 5, 6, and shift E5 to E7, right? Okay. Now, when I shift it to E7, I can just go from it to 0. Because after I did E7, it will go to here when I apply again A, and it will go to 0. When I moved it to E6, it will again go to 0. When I moved it to E2, it will go from E2 to E1, and from E1 to 0. From E1, it will go from E1 to 0. So I have this chain of producing A on the natural base, if you want, the elementary base. So you see that if it happens to the natural base, it will happen to any vector. So I can conclude in the general case for this. So only for E3, I have a chain length of 3 times that I need to apply the matrix, namely A to the power of 3, in order to get to 0. For E5 and E4, I need just twice. For E1, E6, E7, E8, for example, E8, I need just 1 to get to 0. But for E3, for example, I need to go from here to E2, from E2 to E1, from E1 to 0. So this is the largest length. I need A to the power of 3 in order to annihilate it, to make it 0. This means that A to the power of 3 takes every vector that it will get and 100% will move it to the 0 vector. So this matrix to the power of 3 will be just the 0 matrix because it annihilates any vector. This is the definition for the matrix vector. As you can, the 0 matrix. As you can see, if we even calculate immediately, we see that A to the power of 3 is indeed the 0 matrix. Okay, so this was a very important uh, kind of question that you not always need to directly take the power of the matrix. It will be quite not nice over here, very many calculations. If you understand the geometry or the algebraic structure of the matrix, it may help you understand how to solve it. And in this example, how to understand if it's the nilpotent matrix and what its index. It's not very easy, but this is a case. This is a nice case. Okay, so we continue with nilpotent matrices. The next thing that I want to talk to you about is that a nilpotent matrix is never, ever. Nilpotent matrix is never invertible. And why is this? This is because we said that there is an eigenvalue that equals 0. As a fact, all its eigenvalues equal 0. Therefore, the determinant of A will be the, as we said, the multiply of all its uh, eigenvalues, and this is 0 times 0 times 0, depends what the index, what is the number of order of the matrix is. So the determinant must be 0. And if a square matrix has a determinant of 0, it means that it's not invertible. I'm sure that ChatGPT will be able to show you this much more clearly, and used something else. Some positive where f suppose an invertible there exists. If it's invertible, this also should be I, but you get I equals 0. This is the contradiction. So if you, what ChatGPT said, that if you assume that there is an inverse, for example, for n, for a nilpotent matrix n, where n to the power of k is 0, so you should get n minus 1, n inverse equals I, but then just raise it to the power of k, and you'll get n inverse k, and k equals 0 times something, which is 0, but if you took this and raised to the power of k, um, okay, I'm sure it is that way, but you just multiply both sides. You take n to the power of k equals 0. Okay, I'm not going to get into it because it took here n to the minus 1 k. Not like this. Let's go on. Okay, so what I wanted to show you is it's not invertible, but I wanted another, I must say that I wanted another proof. I didn't like this proof. Determinant like, this is what I wanted to show you. The determinant must be 0, and a matrix invertible if and only if the determinant is non-zero. So because it's 0, it cannot be invertible. I think this is the most simple proof for proving that any nilpotent matrix is not invertible because it has 0 eigenvalues. Okay. So the next thing we want to talk about nilpotent matrix is its nilpotent matrix. You can triangulize it. I mean, there is a triangular form for a nilpotent matrix. And why is this? This is because remember that the characteristic polynomial, let's call it P of x, is x to the power of some k, for k the order of the matrix. So it means that the characteristic polynomial divides two linear terms. And if so, it means that it can be, the matrix can be triangulated. Because if you remember, if I can show that the characteristic polynomial of a matrix can be separated into linear terms, so it can be inverted, it can be triangulizable. For example, above C, above the complex space, every polynomial can divide it into to its terms. But for example, above the real numbers, you cannot take, for example, x squared plus 1, or yeah, and find its roots because there are complex roots. So nilpotent matrix must be triangulizable. You can see that A is nilpotent, there exists such that no, but I want over the reals. Over C, every matrix is diagonalizable. It's not helping me. Over the reals. But over the reals, it's also, see that it's still triangulizable. Again, it's because the characteristic polynomial can be separated into different terms, right? Or maybe you'll say this more accurate than what I say, but I want you to see this if it will be enough nice to answer me. I don't think it's enough nice. It's not working. That's a problem. Okay. You can see that the characteristic polynomial like this, and for nilpotent matrix, as we said, it's x to the power of n for an n-to-n matrix. It splits completely over R. This is the point. And a real matrix is diagonalizable if the characteristic polynomial split into linear factors over R. So, and every nilpotent matrix will be able to be split into linear factors because this is the characteristic polynomial to some arbitrary n. So it must be able to split even over R's, the real space. So a nilpotent matrix must be diagonalizable. Okay, so this was an important key factor. You can't triangulize every nilpotent matrix, but you cannot diagonalize it. You cannot diagonalize it. And why is this? Wait, let's come back. You cannot diagonalize a nilpotent matrix because if you think about it, Think about minimal polynomial, okay, of a nilpotent matrix. Look at it for a minute. This will tell you why you cannot, except for the case that the nilpotent matrix is the zero matrix, you cannot diagonalize a nilpotent matrix. And this is why. As you can see, the minimal polynomial, as you know, must divide characteristic polynomial, and it's the minimal power polynomial that annihilates the matrix. But the power, but the minimal polynomial equals the characteristic for nilpotent matrix. Okay, so you can see that the minimal polynomial of nilpotent matrix doesn't have to be the same as the power for the characteristic polynomial, because a characteristic polynomial is to the power of something that you may be under, namely, you may, oh, wait, you may have, for example, oh, I don't see anything. You may have, for example, a to the power of n, which is the characteristic polynomial. Let's call it c of x, okay? But even smaller number, so for the characteristic polynomial, we will have a to the power of k, where k is under m. You can get it. So the minimum polynomial doesn't have to be equal to the characteristic polynomial. And more than that, if the matrix is not the zero matrix, the power k for no a equals 0, k is greater than 1, because a to the power of 1 won't be 0 because it's not the zero matrix. So except for the zero matrix, k must be greater than 1. And if you have repeated roots in the minimal polynomial, you need to remember that this means that the matrix is not diagonalizable. So it means that every nilpotent matrix will have a minimal polynomial with repeated roots, because the only term in the minimal polynomial is x to the power of something in nilpotent matrices, because it must divide the characteristic polynomial. The characteristic polynomial is x to the power of n. So it's the minimal polynomial is x to the power of k, but if it's not a zero vector, it won't be. And remember that the matrix annihilates its minimal polynomial, like the characteristic polynomial. The minimal polynomial is the minimal polynomial that the matrix annihilates. So it must be k greater than 1. So the minimal polynomial has repeated roots, but if a matrix has a minimal polynomial with repeated roots, it must be that it's not diagonalizable. So a nilpotent matrix, except for the zero matrix, is not diagonalizable because the minimal polynomial has repeated roots. Okay, this was a very important thing to say. Now for similarity. Now for similarity. I mean, think about it. If I have a nilpotent matrix, okay? And now I know that B is similar, let's call it, to A. Will B be a nilpotent matrix? Namely, does similarity preserve the nilpotency property? And the answer is, think about it. Think about the characteristic polynomial of A. If A is similar to another matrix B, will the characteristic polynomial be the same? The answer is strictly yes. Similar matrices, they have the same characteristic polynomial. It means that x to the power of something, x to the power of n, let's call it, is the characteristic polynomial of A, namely, and because Cayley-Hamilton, A annihilates the characteristic polynomial. So a to the power of n equals 0. So, of course, this is a nilpotent matrix. But if it's similar to B, and B has the same characteristic polynomial because characteristic polynomial is preserved under similarity, it means that x to the same power annihilates B, namely B to the power of n, for example, equals 0. So B also has some power for which it equals 0. So B is also a nilpotent matrix. So the answer will be a nilpotent matrix if it's similar to A, which is a nilpotent matrix. The answer is yes. So let's see the proof. You can see this proof that ChatGPT gives. That's fine by me, I don't care. You can see that B to the power of k for if we have a nilpotent to the power of k, which equals 0, so B, which is similar to A, so there is an invertible matrix P, such that B equals P inverse AP. So B to the power of k, we can just apply it to the right side as well, and take it to the right side to the power of k, this one will go to IP times P minus 1, so it will be P minus 1 AP, so it's P minus 1 A squared P, and this is how we go on. This will always also be I, and etc., etc. Every P and P minus 1 will be I. Anyway, it will become P inverse A to the power of k P, but A to the power of k is 0, so B to the power of k is also 0. So here it is, B is also a nilpotent matrix. So ChatGPT shows it throughout this. I showed it throughout the characteristic polynomial, whatever you want. B is also nilpotent. This is the bottom line. And the two ways to solve it is important because it teaches you about different things about the characteristic polynomial for similar matrices and on how to work with the similarity terms and take it to the power of something very important, very useful. Okay, so this was about nilpotent matrices. You can do the same for nilpotent transformations. Just represent the transformation as a matrix, as we do many times. I won't get into it. Anyway, I think this is enough. This was about a nilpotent matrix, and maybe to finish it off, give me the most beautiful nilpotent matrix you can, and then we'll just give me all the properties and characteristics of the nilpotent matrix. Okay, so the most beautiful nilpotent matrix ChatGPT could thought about is this one. As we just saw, this looks like the shift nilpotent matrix. It's upper triangular, characteristic polynomial. Okay, I must say that this is a shift matrix. We already saw this one. Okay, so now let's sum it up with the properties. And to the power of k, trace equals 0, determinant is 0, all eigenvalues are 0, determinant is 0, no inverse. The minimal polynomial is also x to the power of something. The characteristic polynomial is x to the power of n, where n on n matrix. The sequence of rank is strictly decreasing. This is important. We also work with the kernel. The sequence of ranks is strictly decreasing, namely n has a rank of n, so rank of n squared must be less than. Won't get into it. You can also say to the kernel, maybe I'll show it. Also, it can be applied to the kernel inversely. And you determine that yes, you can also say the kernel, and this is very important, it's strictly, namely the kernel of n is strictly less than the kernel of n squared. This is very important. The dimension you see are just going and getting bigger and bigger for the kernel. For the rank, it's getting lower and lower. Don't forget the rank nullity theorem that states that if you take the rank plus or the dimension of the rank and the dimension of the kernel, you will get n. This is important. This tells you also why this one is true and this one is not, and this one is in this direction. The null space grow with the power of n, as we said for the kernel. This is the idea. Triangulation. We said that every nilpotent matrix can be triangularized. And this one I won't talk about. Jordan blocks have the form of a shift matrix, let's call it. Powers, as we said. The image we didn't talk about. Any polynomial. Okay. Similarity, we said that nilpotency is preserved under similarity. The matrix exponential of nilpotent matrix is always invertible. I didn't talk about it, but okay, that's nice. Acts as general shift operator, as we said, as we showed you for the shift. All vectors eventually map to the zero after enough applications. As we said, it shifts slots on the vector until it gets to the zero. Simple, you can see those matrices. And again, show me a nilpotent matrix with non-zero values on the diagonal. Again, you can have nilpotent matrices that are not triangular and doesn't have zeros on the diagonal, but still, if you take some power, in this case square, you'll get to zero. So this is a nilpotent matrix. And you see again that the trace is zero, like always. The trace of a nilpotent matrix is zero. So this is an important thing to remember. Okay, so this is it. This sums up all the idea of the nilpotency, nilpotent matrices that I wanted to talk about. I didn't talk maybe enough about the relationship between nilpotent matrix and its Jordan form. I want to go to talk about it too much. For any square matrix under algebraic clause, you can look at it. Where in this, and look that on the Jordan form, on the diagonal, you have the eigenvalues. But remember that the eigenvalues of a nilpotent matrix are zeros. So here you will have zeros. So where nilpotent Jordan, a matrix nilpotent, all eigenvalues are zero. In the form so all Jordan blocks of n correspond to eigenvalue zero, as we said. So this will look like this. Okay. This is like the shift, as we said, chain of generalized eigenvectors. Okay. Nilpotent matrix, all zero, all blocks of eigenvalue zero to the power, also zero, determined by largest. Never mind. Okay, so thank you very much. And this was it about the nilpotent matrix. Thank you all. I wish it was very calm and you could just get it and understand all the things we said. Thank you all very much. If there are any mistakes or corrections, please write it down so other will be able to look and see if something is wrong. And thank you all. This was about nilpotent matrix, and that's it for now. That's it.